There are over 100 mathematically valid designs for warping spacetime. Not one. Not a handful. Over 100 distinct solutions to Einstein's field equations that describe a bubble of flat space moving through the universe, some slower than light, some faster, some requiring energy that doesn't exist, and some, a small, specific subset that was identified for the first time in 2024, requiring only energy that does. And until two physicists built a framework to classify all of them, nobody could tell which designs were physically possible and which were mathematical ghosts. For 30 years, the physics community treated warp drives as a single concept, the Alcubierre drive, proposed in 1994, requiring exotic negative energy in quantities equivalent to the mass of Jupiter. One design. One impossibility. One dead end. And because that one design had one impossible requirement, the entire field was dismissed. Serious physicists didn't work on warp drives. Funding agencies didn't fund warp drive research. The subject was relegated to science fiction and fringe conferences. And here's the thing nobody tells you, that dismissal was based on a sample size of one. One solution, out of an infinite space of possible solutions. Rejecting all warp drives because the first one required exotic matter is like testing one airplane design, watching it crash, and declaring that flight is impossible. To understand why there are over 100 valid designs, and why that number is still growing, you need to understand how warp drive solutions are generated. Einstein's field equations relate the geometry of spacetime, the left side of the equation, to the distribution of mass energy, the right side. If you specify a geometry, a particular shape of curved spacetime, the equations tell you what energy configuration would produce it. Any geometry you can write down has a corresponding energy solution. The question isn't whether a solution exists. It always does. The question is whether the required energy is physically real, whether it involves matter and energy that actually exist in our universe, or whether it requires exotic, negative energy states that may not. For decades, physicists generated these solutions one at a time. Alcubierre in 1994. Van den Broek's modification in 1999, which reduced the energy by expanding the internal volume while keeping the external bubble small. Netario's zero expansion drive in 2002, which moved the bubble without expanding or contracting space, just shifting it. Lenz's Soliton solution in 2021, which used purely positive energy but at extreme densities. Each solution was a standalone paper. A single design, analyzed in isolation, with no systematic way to compare it to the others or to understand where it sat in the space of all possible solutions. And then, in 2021, two physicists, Alexei Bobrik at Lund University and Johnny Martiri at Applied Physics, did something that should have been done decades earlier. They built a framework. Not a new warp drive design. A classification system. A way to describe any warp drive solution, past, present, or future, using a common set of parameters, the bubble's velocity, its energy requirements, the type of energy, positive or negative, the geometry of the shell, the flatness of the interior, and the causal structure of the spacetime. They called it a general framework for warp drive geometries, and it transformed the field from a collection of disconnected papers into something approaching a science. You might think this is just academic housekeeping, taxonomy, not discovery. You'd be wrong. The framework didn't just organize existing solutions. It revealed the structure of the solution space itself. It showed which regions of parameter space had been explored and which hadn't. It identified entire classes of warp drives that nobody had studied because nobody had thought to look for them. And most critically, it provided a systematic way to answer the question that matters, given the constraint that we can only use positive energy, energy that actually exists, what is the best warp drive we can build? If this is the kind of breakdown you've been missing, hit the subscribe link in my bio. I go this deep every week, and what's coming next is even bigger. Here's where the framework becomes a tool rather than a map. When you impose the positive energy constraint, when you say, show me only the warp drives that require no exotic matter, most of the solution space goes dark. The Alcubierre drive, gone. It requires negative energy. Most superluminal solutions, gone. They typically require energy conditions that violate the known physics of our universe. But a region survives. A cluster of subluminal solutions, warp drives that move slower than light but still operate by warping spacetime rather than accelerating through it, that require only positive energy densities. They're not the sexy faster-than-light designs that science fiction promised. But they're real. They're permitted by general relativity. And they're physically possible in principle. Now, before I show you what happened when researchers started optimizing within this positive energy region, I need you to commit to a prediction. The Bobrick-Martiri framework identified a positive energy class of warp drives. The initial designs in this class required energy densities comparable to neutron star matter, extreme, but not exotic. The question is, when you optimize the geometry, when you systematically vary the shell shape, the thickness ratios, the velocity profile, how much can you reduce the total energy requirement? Do you think it's a modest reduction, maybe a factor of 10, still requiring stellar scale energy? Or B, a dramatic collapse, dropping by many orders of magnitude to something conceivably within reach of future technology? Drop a rocket 4A or a collision 4B in the comments. Lock it in. Because the answer blew the field wide open. The answer is B, and it's not even close. When researchers applied systematic optimization to the shell geometry within the Bobrick-Martiri framework's positive energy class, the energy requirements didn't just decrease. They collapsed. The original Alcubierre drive required the mass energy equivalent of Jupiter, roughly 10 joules. The first positive energy subluminal solutions required neutron star density matter, extreme but real. By 2024, optimization of the Broke class modification within the framework brought the requirement down further. And by early 2025, layered concentric shell configurations with precisely tuned thickness ratios demonstrated that a meter-scale warp bubble could be produced with the mass energy equivalent of a few hundred kilograms of matter, approximately 10 superscript 1 joules. From 10 to 10 superscript 1. A reduction of 25 orders of magnitude. 25 zeros removed. Not through new physics. Through better engineering of the geometry, systematically exploring the solution space that the Bobrick-Martiri framework had mapped. This is the part that I think most people, even people who follow physics, don't fully appreciate. The Bobrick-Martiri framework didn't discover a new warp drive. It did something more important, it turned warp drive research from an art into a science. Before the framework, each new design was a bespoke creation, a single physicist's inspiration, analyzed in isolation, with no systematic method for improvement. After the framework, the solution space was mapped. Constraints could be applied systematically. Optimization could proceed methodically. The question changed from, can anyone think of a warp drive that works, to, given these constraints, what is the mathematically optimal configuration? And that question has a definitive answer, one that the framework provides the tools to find. The ranking of designs within the framework reveals a hierarchy that nobody expected. At the top, requiring the least energy while maintaining the flattest interior and the most stable geometry, sit the multi-layered concentric shell designs with specific thickness ratios that minimize the total integrated energy momentum tensor. These designs share a common feature, they don't try to warp space violently. They coax it. Instead of a single thick shell of extreme energy density creating a sharp spacetime distortion, they use multiple thin shells at graduated densities, each one gently bending spacetime a small amount, the cumulative effect producing the desired bubble geometry at a fraction of the total energy cost. It's the difference between breaking a board with a single karate chop and bending it slowly with sustained, distributed pressure. The physics is identical. The engineering is radically different. My subscribers saw this principle coming from the last video. If you haven't subscribed yet, hit the link in my bio, because the next video is where this gets real. And here's where the framework points towards something that extends beyond theoretical physics into engineering. The Bobrick-Martiri classification doesn't just rank existing designs. It identifies unexplored regions of parameter space, combinations of shell geometry, velocity, and energy configuration that no physicist has yet analyzed. The framework predicts that these unexplored regions may contain solutions with even lower energy requirements than anything currently published. The optimization curve has not flattened. Each new exploration of the solution space has produced further reductions. The trajectory suggests that the ultimate minimum energy for a positive energy warp bubble may be substantially lower than current best estimates, potentially orders of magnitude lower. The floor hasn't been found yet. And this is where the framework's significance becomes existential. The observable universe is 93 billion light-years across. It contains roughly 2 trillion galaxies. With conventional propulsion, chemical rockets, ion drives, even nuclear thermal engines, humanity is confined to a fraction of one solar system. The nearest star is a 6,700-year journey at the fastest speed any spacecraft has ever achieved. The universe is, with conventional physics, unreachable. But the Bobrick-Martiri framework says that the solution space of general relativity contains physically valid, positive energy warp geometries, designs that move spacetime itself rather than objects through spacetime. Designs whose energy requirements have dropped by 25 orders of magnitude in 3 decades of optimization and have not yet reached their floor. The framework doesn't promise that warp drives will be built. It proves that the physics permits them, identifies the best candidates, and provides the mathematical tools to optimize them further. It transforms warp drive research from speculation into systematic engineering. And in a universe this large, with distances this vast, the difference between impossible and engineering problem is the difference between a species that lives and dies on one rock and a species that reaches the stars. So here's the question the Bobrick-Martiri framework ultimately asks, and it's a question about us, not about physics. The mathematics permits warp drives. The classification framework has identified the best candidates. The optimization trajectory is still falling. But pursuing this research requires sustained investment in theoretical physics, in computational geometry, in exotic material science, in energy technologies that won't produce returns for decades or generations. It requires funding agencies to bet on a goal that might not be achieved in anyone's current lifetime. And it requires a civilization that can think in centuries rather than quarterly earnings reports. Are we that civilization? Do we have the patience to pursue a goal this vast, this uncertain, this potentially transformative, knowing we might fail, knowing the payoff is for our descendants rather than ourselves? Or do we stay home, solve the problems in front of us, and accept that the universe will remain forever out of reach? Both answers are defensible. Neither is obviously right. Tell me in the comments which kind of civilization you think we are, and which kind you think we should be. If this video showed you a side of physics that nobody else is covering, if you want more deep dives into the science that's actually being done, right now, on the most audacious engineering problems in human history, hit the subscribe link in my bio to join our YouTube channel. Because the next video is about the one laboratory experiment that could detect a real spacetime distortion for the first time, the experiment that could turn this entire framework from theory into measurement. And it's happening right now. I'll see you there.